of light and sound. Refraction is the bending of light. Okay? I want you to think about a scenario. I know if you look out in the parking lot, you might see a few people that like to go off-roading. Okay, so they have a truck. Imagine this is off-roading. Instead of thinking of this as light, I want you to think of it as asphalt and grass. Okay, so somebody's going to drive in with their truck and go from nice, fast asphalt and then hit the grass. Well, what's going to happen? Okay, if you have this car hitting the asphalt, what wheel is first going to hit the grass?
The left one.
The passenger side, right? The passenger wheel right here is going to hit the grass.
Yes.
Yes? Okay. And the driver's side wheel is still going to be on the asphalt. What do you think's faster driving? Asphalt or grass? What's faster? Asphalt, right? That's going to be faster. So what you're going to have is this. You're going to have one tire that's going to be a lot slower and one tire that's faster. What would happen if you have one tire slower, one tire faster? What's going to happen with that car? It's going to turn, right? And it's not going to spin all the way out, but what's going to happen is it's going to go slow. You have slow and fast, so you're going to turn the car until that driver's side wheel hits the grass. And then both are in the grass and it's going to go the same speed. Does that make sense? Okay, well that's the same exact thing that happens with light. So when you have a ray of light that comes in at an angle, some of the rays are going to get bent first, are going to be slowed down first. If this is glass and this is air, or let's say water, okay? What's going to happen is some of the rays of light are going to get slowed down first, and you're going to see an image get bent as it travels through that new surface. So all the action happens right at the surface, between a thinner and a thicker, or vice versa. That's what we call refraction. Alright? I'll pause again. Wait, did we ever start? Okay. Yeah. So that's refraction, right? If you ever paddle a boat, you'll see the oar is going to be bent for some reason. It's just refraction. Okay? And these two scenarios are water is going to be thicker than air, so you're going from thinner to thicker. It's going to get bent inward. Okay? It's hard to tell this way. It looks like it the other way, and I'll explain why here in a second. But here are the three scenarios you need to know. When an object goes dead on, think in all three scenarios, okay? Will, I want you to think about your car tires hitting the grass. If you go head on, both tires hit the grass at the same time. They're both going to get slowed down at the same time. There's going to be no bending. So if you go in at 0 degrees difference, there won't be any bending. However, if you go from thinner to thicker at an angle, you're going to get bent inward. And if you go from thicker to thinner at an angle, you're going to get bent outward. And I'm going to ask you these questions on a test, okay? I'm going to, I might be talking about index of refraction, which you're going to talk about. Actually, no, I'm just going to talk about thicker or thinner. Just think about car tires, okay? Just think about the grass and the asphalt. And I talk about thicker to thinner, it's going from grass to the asphalt. If it goes from thinner to thicker, then we're talking about from the asphalt to the grass. Okay? Alright, I'll pause because this is going to take a little while to copy. Here, beaker into this corn oil. What do you think is going to happen? Is it going to enlarge? Is it going to get smaller, or is it going to disappear in the thin air? Are we ready?
It's smaller.
Here we go.
I'm scared.
What do you think so far?
Black magic.
It disappeared.
Disappears.
He was right.
Oh!
How did you know?
Disappeared. Cool, huh?
Can you do that again?
Yes. Oh, you decided to wake up for it?
It got so
We'll do it again.
It's been so much. Expanded so much that it looks like it's not.
Yes. No. Here we go. Let's try it again. Ready? So you got this? You watching this time? Yeah.
I'm not hiding.
You see stuff on.
You see the line.
The writing.
If it was clear, if they were both clear.
You thought ahead and got clear.
Cool, huh? Yeah? Yeah? So, you could do this as a party trick too. Take a glass, take a glass. You got to make sure it's the same type of glass as this. Okay. Take a glass and you roll it in a towel, shatter it up, pour it in the oil, and then have another glass that's the same type and pull it out of the oil, make it look like you put it back together. Magician's secrets revealed. All right. Moving on. We'll pause there. I want you to copy these numbers down. Just say indices of refraction and these numbers here. All right. Air. The higher the number, the slower the material or the slower light will travel.
What?
Yes. I want you to say indices of refraction, and I want you to do air equals 1, water equals 1.33. Okay? So here's the deal. Air is basically, that's the same thing as going through a vacuum. Okay? Air maybe is really like 1.0003, but we'll just say 1. Okay? So as the index of refraction gets bigger, the light travels slower. Okay? So the light going through a diamond is one of the slowest materials that light will travel through, is a diamond. Okay? And it's a whole lot slower. I mean, think compared to water, it's almost twice as slow as when light travels through water. When light travels through air, it's 1. It's more than twice. It's 2.5 times slower when it goes through a diamond as it does go through air. Okay, so light will travel slower when it goes through different substances. Okay? Now, so the reason that happened with the oil is because the index of refraction of the oil is equal to the index of refraction of the glass we're using. So that's why you can't see the glass, because they have the same index of refraction. So the light's not going to bend back and forth when it goes through it. Cool, huh? Yeah?
Yeah.
Okay. All right. Can I move on?
No.
Or I'll wait. I'll wait and we'll pause.
Apologize.
Remember what I just said. So think about that. Think about that truck that's going now from the grass to the asphalt. Okay. So now we're going from thicker to thinner. All right. Now remember, it bends away. So if I'm going from the grass here, when I get to the asphalt, I'm going to turn away. All right. If I go a little bit further out, I'm going to turn away more. I'm going to go further out, I'm going to turn away more. Sooner or later, because you're going from, you're going to have a smaller angle than a bigger angle, sooner or later you'll get an angle here that's going to cause that angle to be 90 degrees, which means the light's going to get trapped along the surface. Okay? We call that causes this angle there, okay, to be 90 degrees. So here's your critical angle that causes this to be 90, which means the light's trapped along the surface. Has anyone done any diving underwater?
Yeah.
You dive underwater and ever look up? If you look up, what you're going to see is, if you look straight up, you're going to see the boat above you. You're going to see stuff outside the water. But once you go past a certain angle, it's going to be completely dark. It's going to be a reflection going back into the water.
You can see it.
And the idea is this. And actually, you can even do this if you stand next to an aquarium, a fish tank. If you look into a fish tank and look up at the water, there's going to be a certain angle where all of a sudden you'll just see reflection back into the aquarium. Okay? And what that is looking past this critical angle. Because once you go past the critical angle of water is about 48 degrees. So I see everything, and once I get past 48 degrees, then now it's going to be just like a mirror. And so there'll be a circle around me that's within the 48 degrees, but as soon as I get past the 48 degrees, it's going to be a mirror bouncing back in. Okay? And I won't be able to look outside that water. Okay? You hit the critical angle will cause that ray of light to bend all the way to 90 degrees, so it's trapped along the surface. Okay? Alright. Can I move on here?
No.
Again, don't copy word for word. Okay, I want you to get a general idea. The critical angle causes the refracted angle to be 90 degrees. So we'll pause then. I mean, all the light is going to bounce back in. Okay, so here we go. Here is a light beam that's going through glass and is bending out. It's going from thicker to thinner. Is it hard to see?
Yeah.
Want me to turn the light off? There you go. Isn't that cool? All right. Here's a light beam. It's going. This is glass right now. This is a half moon of glass. All right. And as the beam of light exits the glass, it's going from thicker to thinner. It's going to bend away. Okay. So it was going in at 25 degrees and it's coming out at like 33, 36 degrees, something like that.
What about the little faint line that's going down?
Yeah, and there's a little bit, and it's because nothing's perfect, and there might, I don't know if there was like a, if there's something near there, I don't know. But yeah, there's imperfections with some of the stuff. Now, here, we're getting close to that critical angle. So again, there's some imperfections here, some imperfections there. Okay? So we're at around the critical angle. Once, and that's about 38 degrees. Once you go to 50 degrees, look what happens. The light is completely trapped and is getting completely reflected back down into the surface. Okay? So that's like the divers trying to look up. Alright? Once you go past an angle, depending on the surface, the thicker the surface, the smaller the angle. But for water, it's about 48 degrees. Once you go past 48 degrees, it bounces back in. For this glass, it's about 40 degrees. Once you go past 40, it bounces back in, and you get a reflection, just like a mirror. It's going to be just like a mirror with total internal reflection. Okay, now, this alone is very useful. Okay? First off, have you ever noticed a pool at night, how it seems to like glow? You know what I'm talking about? Right here. If you go to a pool at night, all the lights are going to be on the side, and that's probably for safety too. But the idea is this. When you have a light on the side, rays of light that are, if they go up straight out, they're going to be within the critical angle and they'll be able to escape. But rays of light that go a little bit further out and get past the critical angle are now going to bounce back to the surface. So the reason it looks like that pool is trapping the light in is because it's trapping the light in. Okay? The light past the critical angle has to bounce back into the water, into the pool. Okay? And that's why these pools seem to glow at night. Because it's keeping a lot of light from those light sources in. Okay, these are just a couple of my pools in my summer homes. Sure. This is the Hamptons.
Oh,
This is
Hamptons.
Yes. Okay. Now this one, I believe this is my Florida home. Do you see the streams of green light coming through here? What that is they just have like little fountains that are spraying into the pool.
Is that dirty water?
Huh?
Yeah, because my pool does that too.
But here's the deal: with these streams, or the water coming in, what they have is a light here, and because that stream is thin enough, the light is getting trapped. Notice how the light's coming from the ground over here, and it's trapped in the water as it goes in the pool. Okay, so as it goes through that stream, the light stays past the critical angle and it keeps bouncing within the water, so it doesn't get to escape. And now there is a little bit of escape because you can see the light, but this is the idea of fiber optics. Okay, do you know the fiber optics that you see like at Spencer's, a little plastic hair that you shine a light and it comes out the other end? It's in Christmas trees too. You know what I'm talking about? Some Christmas trees have a fiber optic so that it's not a bulb they have to worry about. Well, the idea of fiber optics, if any of you have FiOS, the fiber optic signal, okay? I actually don't know what the S is, but I'm guessing signal. Alright. What the idea with FiOS is, that's the really high-speed internet. And with FiOS, if you have cable, if you get your internet through cable, what you have is you have a copper wire, and they're turning electricity on and off, on and off, on and off. And that's fine, that's really fast, but with that you can lose energy the longer the wire is, and it's a little bit slower with turning on and turning off with copper. With FiOS, with a fiber optic cable, what you have is there's this tiny, thin piece of glass that's going to your house. Okay, and basically there's a guy from Verizon on one end turning a light on and off. Okay, obviously it's a computer, but you have the lights turning on and off from Verizon, and because this glass is so thin, okay, it's always past the critical angle, and the light can never escape until it gets to the end. And at the end, they have a 90-degree cutoff, and they have a plug, and the light can finally escape. Okay, that's why I notice these are good fiber optic cables. Notice how there's no light escaping from the sides. They only escape on the ends. Okay? This was my old job before I became a teacher. Before I was a teacher, I worked for a company that had to run fiber optic cable. And like it was all in this building, so I had to connect from like AT&T to server, you know, whatever's going to be, eBay or something like that. And when we ran the fiber optic cable, you had to be really, really careful because, you know, these were all insulated. And so you'd have all this insulation around it, and if you ever dealt with any kind of wiring, you got to strip a wire to put a plug on it. Well, what would happen is we'd strip the wire, and we had to be extremely careful because you have this very, very thin piece of glass. And if you put your finger up to a fiber optic cable when there was no insulation on it, when you put your finger up to it, you would never feel the pressure on your fingertip. The fiber optic cable will go straight through your skin without you noticing until it hit a nerve. And then you'd pull your finger back and you'd have a piece of glass stuck in your finger for a long time. Okay? So you had to be really, really careful with fiber optics because of this thin piece of glass. And the other part was that when we ran the fiber, we couldn't curve it or bend it too much. Because when you curve fiber, for one, it's glass, so if you curved it too much, obviously it would break on the inside and you're in trouble. Okay? But the idea is that still, even if you bent it enough where it wasn't going to break, you might be past the critical angle. If I bent this cable a little bit more here, this light might be able to go within the critical angle and actually escape. Okay, so you have different types of fiber optics had different turning radiuses to them to make sure you don't lose a signal. But this saves a lot more energy than, say, using a copper wire. Okay. Diamonds. Same thing with diamonds. Okay, this is a diamond. This is like quartz. With a diamond, again, we said the index of refraction of diamond was 2.42. It was really, really high. Where quartz or glass is maybe around 1.5. Okay, so glass will not trap light as well as a diamond. If you put a diamond and a piece of glass next to each other and they have them cut the same way, the diamond will just seem to glow, like it has so much more light trapped in it than glass will. And the reason that's the case is because, again, it's trapping light in. Okay, with a diamond, you'll have light coming in from the top, and maybe it tries to escape through the bottom, but it'll be past the critical angle, and it's going to bounce away. Then it hits over here, again, it's past the critical angle, and it reflects back in. So diamonds, the 4 C's for diamonds are cut, clarity, carat, and color. Cut is important. Okay, the way you can cut a diamond might help with getting more critical angles so that more of the light is going to be trapped inside that diamond. Okay? Alright. This is how a mirage works. I want you to think about a mirage. You're at a 4th of July parade, okay? You look way off in the distance at the band coming down, and you see on the ground it looks like water. Okay, more the cartoon version of it. You're out in the desert. You look far, far away, and then way out in the desert, you see this beautiful blue water, right? You run towards the water. As you get close to the water, it disappears. It was a mirage, right? This is just like you looking out from water, or the diamond, or the pool. But in this case, what you have is, on the surface of that sand, okay, you're going to have really, really hot water on that hot day, or on the road, you're looking at the parade. Because the asphalt's going to be so hot, you're going to get much hotter air right along the bottom of the ground. Okay, right along the sand, right along the asphalt. Alright, so what you have is you have really, really hot air and a little bit cooler air. So you have thicker substance and thinner substance. So just like the water trying to escape a pool, now it's upside down. The ray of light now is trying to escape into the thinner air, but it's going to be past a critical angle. Okay, it only happens when you look really far away at a really high angle, right? You're looking past a critical angle. So the reflection bounces back up. So if I'm standing here, I think I'm looking at water down below. What am I really seeing? What's beautiful and blue that I'm really looking at? The blue sky. So a mirage is just a reflection. This is also how a prism works and how you get rainbows. We all know, right? Isaac Newton is the one that found out that white light is really all the color. We found out that each ray of light, each color, bends differently. So when white light travels through glass, red will bend just a little bit. Orange will bend just a little bit more. Okay, yellow a little bit more, green a little more, blue, indigo, violet. So violet bends light or refracts a lot more than red does. So the reason that you can get a rainbow is that as glass travels through and you know they make it a triangle to help this, when you get that refraction, the red light won't bend as much as the violet will, and it gets spread out. And so that's how a prism works. I'll let you copy that. Polarizing lenses! Last thing I want to talk about. I'm going to turn the lights on for this one.
Another trick to impress the ladies.
The lights! Okay. Here we go. Polarizing lenses. There are certain things out there that can polarize. Where is my... Man.
You know what I mean?
No.
It's like this guy had in the air, like hanging, and then he let go, and like the bottom part didn't touch the floor yet until like the other part came
Oh,
out.
the middle
Alright.
connected.
But it was like slow motion, so I don't know.
Okay. Here,
Oh, you saw that one?
light is a wave, right? But light isn't just a wave that goes in one direction. Okay, when light comes off from the electrons and all that stuff, it goes in all different directions. It's all the planes. So here's one plane. Okay? Here's another plane. But light comes out in all the planes. They're going everywhere.
I don't
Okay?
think girls will like this.
And this is what glare is. If you look at the water, if you were, if you were fishing and you look at the water, or you're at the beach and you look out on the water and you get the reflection of the sun, you get all these planes reflecting out, and it's hard to see. Okay? So what you want to do is you want to have something that only lets one plane in. Okay? I only want this part of that light in, not all these planes that are coming in every direction. Does that make sense? Okay? So what we do is we have polarizing lenses. You can let go. Thank you. It's okay. I'll be okay. Alright. So, I know the first time I saw it was for fishermen. Because with fishermen, they're going to be looking at the water a lot, and when they want to look in the water, they want to look in the water. They don't want to see the glare on top. So they were selling polarizing lenses. But now, most good sunglasses, alright, you buy a good pair of Oakleys, you're going to have polarizing lenses on them. Okay, and the idea with polarizing lenses versus cheap lenses is that this is a polarizing lens. And it's not that it's just darkened. But instead, just like the Slinky, light's coming in all the directions, and I'm only going to let one of the planes in. I'm only going to let the plane of light going up and down in. Okay? And it's hard to tell with just one polarizing lens what it is. But it does help get rid of glare. Any photographer will need a polarizing lens. Okay? The polarizing lens gets rid of the glare. Alright? But of course, if you have sunglasses, some window tints will be polarizing. Alright? Now, here's the deal. Here's a way to find out if you have good sunglasses or if you have $7.99, $7-Eleven sunglasses.
Oh, that's the
Okay?
they're polarized sunglasses.
Here we go. So,
You're the way.
if I have a polarizing lens and I put another one in front of it, it's going to be a little bit darker, but they're parallel right now. Okay, so I have this, and then I took another lens and did that. So still that plane going up and down is going to be allowed through. However, if I turn the lens, and now it's perpendicular. So now I have this, and I did that. And now the waves will not be able to go through. Okay? So watch, again, I turn it.
Magic.
Cool, huh?
Yeah.
Bro's
Yeah.
impressed.
So if you wanted to see if your glasses were actually polarizing or not,
These will like it.
you could do this. You could take, if you go to, if you see something that's advertised as polarizing sunglasses, take 2 pairs and just do this. And if you can see through the whole time as you spin it, then those are not polarizing glasses.
Rip you off.
Okay? Yeah, and you have fakeleys, not Oakleys. Now, with that, have you ever noticed my mother-in-law? I remember a number of times where she was filming one of my kids around, and then she come to me and say, my camera's broken. Because she would film like this, chasing my son around, and then she tried to take a picture like that. And she couldn't see the picture anymore on the camera. And I told her to take off her sunglasses. Okay? Because the problem was, the light coming off of a lot of displays only come in one plane. And when you wear your sunglasses and you turn it, your sunglasses are filtering it out and you're not able to see anything. Have you ever noticed in your car, you're driving your car and you look at your car stereo and you have to tilt your head to see the display on the car stereo? A lot of displays are only coming off in one plane. If you're wearing sunglasses that are polarizing, you'll have to turn your head because you might be looking at 90 degrees or and blocking what you see. Have you seen the checkered boards on the glass when you're driving? Have you ever noticed when you're driving along with newer cars, you'll look out the window and if you're wearing sunglasses that are polarizing, you'll see like this checkered pattern on the glass. Again, there's polarized, the glass is somewhat polarized. And of course it's checkered, it's got to have two angles because if you had polarizing glass just going in one direction and you turn your head the wrong way, you wouldn't be able to look outside the glass and that would not be good. Okay? But even with your cell phone, you might look at your cell phone and especially with some of the cheaper cell phones, the display might only be in one direction. So if you look at your cell phone, you might have to turn it because you have your sunglasses on. Okay? Alright, one last thing that I think is kind of cool with it. I have these two, they're blocked. If I take a third lens and I stick it in between, watch this. So if you can turn the other one in between, you can see the light. I'll turn the light off here. See that?
Yes.
This one's in between the other two. There you go. Cool, huh?
Yeah.
So there's polarizing lenses. All right.